In this week's material, we're going to look at the difference between an actual molecule, benzene, and a made-up molecule, 1,3,5-cyclohexatriene. The difference between these two molecules is the fact that benzene is aromatic, and the made-up molecule, 1,3,5-cyclohexatriene, is not aromatic. We're trying to reinforce the idea of aromaticity and talking about why it's stable. And we're trying to realize that aromaticity brings extra stability to molecules and that these rings don't behave like normal alkenes and they have different types of reactions. To begin with, we're going to look at the 1,3,5-cyclohexatriene. Okay, and so if it wasn't aromatic, you would see it would not have resonance and it would be a alternating single, double, single, double, single, double bond throughout the ring. The bond lengths for single are 154 and the bond lengths for double are 134. So what you would end up realizing is that you actually have a lopsided molecule with varying lengths. So the double bonds would be shorter and your single bonds would be longer. And you wouldn't end up with a symmetrical molecule. It would be kind of odd shaped because of this. Okay, so now what you also want to take into account is that there is 2 pi electrons localized here, and there is 0 pi electrons here. And this goes continuously throughout the ring of 1,3,5-cyclohexatriene. The difference with benzene is going to share all of its pi electrons throughout the ring. And that's why you see this circle in the middle of the ring. It helps to visualize that aromatic rings share their pi electrons throughout all of the atoms in the ring. So what we're going to realize here is the bond angles, all bond angles for the aromatic ring for benzene are 140. Now what you'll realize is 140 is in between 154 and 134. This tells us that these not bond angles, but bond lengths is what I meant to say. These bond lengths aren't actually a single bond and aren't actually a double bond. So it's a hybrid of a bond, and it is in between a single and a double bond. This makes sense because the electrons are freely being shared or delocalized through all 6 carbons, and there's no single, double, single bond action going on of alternating bonds. Okay, and so now we're also going to say there are 6 pi electrons delocalized, and what that means is that they are not in one location, they are spread across this area of the molecule, across 6 carbons. Okay, and so we've studied these two molecules. If we had a program that did modeling, we can go ahead and calculate these and see that there is more stability in the aromatic ring. Okay, and it's about 150 kilojoules more stable than the 1,3,5-cyclohexatriene. Okay, so what can we do? We're going to conclude that benzene is real because it is about 150 kilojoules less energetic compared to 1,3,5-cyclohexatriene. Okay, and what I want you to remember is The 1,3,5 cyclohexatriene is not a real molecule. You are not going to be needed to identify it. Okay, it's just something that I wanted to present to show you that aromaticity is different than having alternating double and single bonds.